been waiting way too long. Yeah, I've been down here trying to get it. Yeah, I've been waiting way too long.
This is the video for Geometry 10.3. We're going to be applying properties of chords in circles. Before I get started with our theorems, I need to mention something about chords and the arc. We talked about when we have a central angle that the measure of the chord is equal, the measure of the arc is equal to the measure of the central angle. Okay, well, you need to also understand that it doesn't have to be a central angle in order for there to be an arc. So here is arc AB, noted like this. And it's not necessarily that I can find the measure of that arc, but what I do know is that there is an arc there formed by chord AB, which is a segment that whose endpoints are on the circle. So just understand that no matter where I draw a chord, that chord then creates an arc. It doesn't need to be from a central angle like that. So this first theorem says that in the same circle or in congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. So what does this mean? Okay, so remember, a minor arc is an arc that is less than 180 degrees. And so if I draw a chord here and I draw a chord here, what this theorem is saying is that this is A, B, C, D. Chord arc AB is equal to arc CD if and only if, that's what IFF means, if and only if the chord segment AB is congruent to the chord segment CD. Okay, so if and only if means that both the conditional and the converse are true. So no matter which way you read this theorem, it should still be true. So if those are congruent, then the arcs are congruent. Likewise, if the arcs are congruent, then the chords are congruent. Notice that these are two chords on the same circle, or it would need to be two chords on two different circles that are congruent circles. So they have to be congruent circles if it's in two different circles. Theorem 10.4 says if one chord is a perpendicular bisector of another chord, then the first chord is a diameter. So what does this mean? Okay, so one chord is a perpendicular bisector of another. Remember, a chord has to be endpoints on the circle. So if here is my first chord, call that A, B. If that is a perpendicular bisector of this other chord, CD, what does perpendicular bisector means? That means that this is a right angle and that those are congruent segments. So we're going to call this M. So MD is congruent to CM. So if this is true, then AB, segment AB, is a diameter. Notice that it says a diameter and not the diameter, because there are many ways that we could draw the diameter of this circle. Now, if that is the diameter, which it is because it's a perpendicular bisector, then we know that somewhere on the diameter is the center of the circle. We'll call that X. Okay? So if a chord is a perpendicular bisector of another, okay, which again means that MD is congruent to CM, then AB is the diameter. Theorem 10.5 says if a diameter is perpendicular to a chord, then it bisects the chord and its arc. So it's very similar to what we just said. So let's take a look at this. All right, so here's a picture of the diameter. Segment CD is the diameter. So diameter is segment CD. And it's perpendicular to the chord. The chord is segment AB. And then, so if they are perpendicular, if there is a right angle there, then we know that the diameter bisects the chord, which means AR is going to be congruent to BR. So this will be congruent to that. That's what it means when it says bisect. And its arc. So what is the arc formed by chord AB? The arc formed would be arc AB. And so what this is saying is that now AC is congruent to BC, talking about the arcs. Okay, so if the diameter is perpendicular to a chord, then it bisects the chord and the arc. So now I know that arc AC is congruent to arc BC, just as segment AR is congruent to segment BR. Last one here, in the same circle or two congruent circles, two chords are congruent if and only if they are equidistant from the center. So we're going to call this circle X. This is circle X. And if we have two chords, they're congruent if and only if. Remember, if and only if means that the converse is also true. So if they are equidistant from the center, then they are congruent. Or if they're congruent, then they're equidistant from the center. It goes both ways. So I'm going to draw two chords here. So those chords are congruent if and only if they are equidistant from the center. What that means is that from the chord to the center of the circle, now that has to be a right angle there. Because when I say equidistant, I mean the shortest distance, which has to be at a right angle. So again, those have to be right angles there. And these segments have to be congruent. So if those are congruent, then these chords, chord A, B, and chord C, D, are congruent chords. Or if they are congruent chords, then you know that this distance to the center is congruent on both sides. Again, making sure that that segment forms a right angle with the chord. Otherwise, that's not the shortest distance that we're talking about. So I know that's kind of a lot, but it really helps if you can draw this and state what is true, and we'll be applying these in our problems.
I've been waiting way too long. Yeah.